Welcome to Standex Electronics, where we will be exploring what magnets are and how they are used in the electronic industry. Most of us think magnets are only good for hanging pictures and notes on our refrigerator. On the contrary, magnets are playing an ever-increasing role in the field of electronics. Their applications are growing on a regular basis. We will define the key terms relating to magnets, and we will explore what magnets are, what they do, and how they are used. Let's pose a few questions. What is magnetic? Where does it come from? What is a magnet? Where does the energy come from? What is a dipole? What are the magnet's properties and why do we care? What affects magnets? How does one make an artificial magnet? What is a Curie effect? Are there different types of magnets? We will be answering these questions in the next 15 minutes. Let's answer the first question. What is magnetic? To do this, you will need to go back to your chemistry class in high school. The magnetic effect is created at the subatomic level. Here the atom has a nucleus composed of protons and neutrons with negatively charged electrons circling the nucleus. Two things occur in the atom that produce magnetics. Both occur because of the motion of the electron. Electrons, by their very nature, have a spin associated with them. Similar to a spinning top, the electrons also have another movement. They rotate or circulate around the nucleus of the atom. This is similar to the Earth circling around the Sun as it spins, producing day and night on Earth. As the electrons circulate around the nucleus, they generate an angular momentum. The net effect of electrons' spin and the angular momentum produce what is called a dipole. The net effect of the combination of the electrons' spin and angular momentum produces a tiny magnet within the atom, and it's called a dipole. The dipole's magnetic field is very small and cannot be measured. Most atoms have more than one electron. When two electrons exist in an atom, they will form a pair of two dipoles. The two dipoles are equal and opposite in magnetic strength. The magnetic fields of two electron pairs effectively cancel each other out. With each additional pair of electrons within the atoms, there will be accompanying pair of dipoles. In most elements, the dipoles align themselves with an equal and opposite dipole, effectively canceling out any net overall effect. Shown above are several elements, starting with hydrogen on the upper far left end, with neon on the bottom right. Each arrow represents a dipole. As the elements become larger, the number of electrons increases with a corresponding increase in dipoles. In several more complex atoms, the magnetic effect is not canceled out within the atom. This is the case with many metals. However, when the atoms are grouped together many billions of times over, the tiny magnets produced from the dipoles line up in a random manner within the bulk material, producing no overall magnetic field. This is because, for most metals, their atomic structure locks each molecule in place in a random manner. Iron, nickel, and cobalt are ferromagnetic elements that can occur naturally magnetized in nature. This effect is shown to the right, where the dipoles are all aligned. These are called permanent magnets. Most of the magnets we use in electronics are made into magnets by magnetic technology. The picture above on the right represents dipoles all aligned, producing the overall magnetic field. The dipoles will align themselves and can become locked in place in the crystal's lattice structure. In this case, the material goes from the top right picture to the bottom right picture and remains that way. There are other ferromagnetic materials where the dipoles align when subject to a magnetic field. However, when the magnetic field is removed, the dipoles revert back to their random structure. With this condition, the material goes from the top right picture to the bottom right picture and then returns to the top right picture. All magnets have different properties. The properties of each allow us to selectively use them in different applications. Knowing these properties will better allow us to use the correct magnet in the correct application, enhancing the design. The key properties when using magnets in relays and sensors are the following: ability to magnetize and demagnetize the ferromagnetic material easily and offer magnetic stability at low and high temperatures. Careful selection is critical. Also, magnetic strength and magnet size are also key attributes. Other magnetic properties you will need to be concerned with are Curie temperature, stability, shock, cost, and availability. When magnets are to be used above 150 degrees Celsius, care should be taken to select magnets that are more stable at high temperatures. Probably the most stable magnets at high temperatures are the aluminum nickel cobalt series, and for rare earth samarium cobalt is the best. Most magnets are relatively stable at temperatures of 0 Celsius and below, but for some magnets that is not the case. The above chart offers a quick look at the most popular types of magnets used in the electronics industry and just how stable they are at low and high temperature. No tau ferrite magnets are a bad choice if your application experiences any temperatures below -20 degrees Celsius. Magnetic strength is often important because it is a big factor in determining the distance in which a reed sensor or other magnetic sensor will open and close. The effects of other magnetic fields or ferromagnetic materials from nearby components may affect other magnetic components. For instance, a reed sensor's closure and opening points may be affected by these potential magnetic fields, so any designer will have to take them into consideration. Size will also determine the operate points of a sensor. Sizes can vary dramatically. Potentially, the greatest sensing distance is achieved when matching up the size and strength of the magnet. Rare earth magnets offer the greatest magnetism in the smallest size. The Curie temperature of a magnet or ferromagnetic material is that temperature where the magnetic properties are lost. The temperatures are usually quite high. However, they can and are reached in several applications. In many cases, once the temperature drops below its Curie temperature, the magnetic properties return. This is the case with ferromagnetic materials, or some magnets may lose some or all of their magnetism. Above is a listing of different magnet types and their associated Curie temperatures shown in Kelvin, Celsius, and Fahrenheit. You can see the large variation that exists with different magnets and magnetic materials. Sensing applications requiring accurate, dependable operate and release points require magnets and the magnetic properties to maintain their stability. Any magnetic variations will alter the operate and release points of the context used in the relays and reed sensors. Careful evaluation of the magnet specification needs to be considered as well. A strong shock may slightly change the magnetic strength for a given magnet. If an application calls for an environment involving shock, care must be taken in selecting the correct magnet. Shock can become a factor in a Form B or latching relay, where relay handling at the customer site can cause enough shock to alter the operate points. Iron, nickel, and cobalt are the most common magnetic elements. Less common elements are chromium and manganese. Rare earth types offer very strong fields. Most popular are neodymium and samarium. As with rare earth magnets, there are also a large number of magnets where several elements are combined into a compound that offers improved characteristics. For example, aluminum, nickel, and cobalt are combined to give very stable magnet at high and low temperatures. There has been much speculation about large magnetic fields physically distorting reed switches when the magnetic fields are brought into the proximity of a reed switch or reed switch sensor. In fact, the tiny nickel-iron ferromagnetic blades will reach a magnetic saturation point, and increasing the external magnetic field will have no effect on the reed blades. One can use the analogy of filling a glass of water. Once it is full, no matter how much more water you try to pour into the glass, it will not accept any additional water. Not only is magnetism available in nature, as we have been discussing, and available via man-made magnetic compounds, but it can also be generated via an electromagnet. This is generated by winding copper into a cylinder and passing a current through the wire. A uniform magnetic field is generated in the center of the cylindrical coil. The stronger the current, the stronger the magnetic field. Now that you know where magnets come from, we will now begin to explore how magnets are used in the electronic industry. Magnets are found in abundant quantities in the electronics industry. The largest usage occurs in the reed switch industry, namely in reed sensors and reed relays. Placing a reed switch down the center of a magnetic coil, as shown previously, produces the essentials of a reed relay. The majority of reed relays do not use magnets, but when and where they are used, they represent a critical part of the proper functioning of the reed relay. For reed relays, it is critical to have the ability to magnetize and demagnetize the magnets within the relays that are generally used to make normally closed or latching reed relays. This allows the relay manufacturer to precisely and accurately adjust the magnets for best operating characteristics. For most stable results, the magnet should be fully magnetized and then demagnetized to the best operating point. To make a normally closed reed relay, a magnet is placed inside the coil. It is centered on the reed switch contact gap and in parallel with the switch. For maximum magnetic efficiency, the magnet is placed on the glass of the reed switch. Once in place, each of the two reeds within the reed switch become magnetized, but with opposite polarity. Being of opposite polarity, the north and the south at the reed switch gap attract each other, causing the reeds to close. When the power is applied to the reed relay coil, the magnetic field produced must be at least equal and opposite in polarity of the magnet. The oppositely polarized magnetic field produced by the coil will open the contacts. Removing the coil power, the contacts will automatically reclose. This completes the cycle of how a normally closed reed relay works. What is so effective about a normally closed reed relay is for applications calling for the contacts to be closed for long periods of time, the relay will draw no power. A latching reed relay is accomplished in a similar way, but generally uses two coils. The first coil closes the contacts, and the second coil opens the contacts. The best magnet types to use for reed relays are the aluminum nickel cobalt series, along with sintered magnets, because they are very stable and are best for magnetizing and demagnetizing. These two magnetic groups are predominantly used for the ease of use and relatively small size. Magnets are used exclusively in reed sensors. Every reed sensor application requires at least one magnet. Reed sensors probably use the most magnets of any sensing technology. Reed sensors use all types of magnets when compared to reed relays. Reed sensors use magnets in sensing applications in three different ways. First, as a normally open sensor, which usually uses only one magnet. Second, as a normally closed sensor using two magnets. And third, as a latching sensor where two or three magnets are used. Normally, open reed sensors are the most popular by far. Generally, the reed switch is housed in a protective package and mounted on a printed circuit board or directly wired to an electronic circuit. A magnet is mounted to some moving element where its distance is being sensed. Once the magnet enters the reed switch's sphere of magnetic influence, the contacts will close. When the magnet is withdrawn, the contacts will open. This completes the reed sensing cycle. Normally closed reed sensors are used in applications where the contacts will be closed for long periods of time. In the normally closed state, the contacts draw no power. This is not the case for solid-state sensors that require power all the time, whether they are in the normally open or normally closed state. Two magnets are required for proper operation. For proper operation of a normally closed reed sensor, a magnet is mounted and centered over the contacts, causing the contacts to close and remain in the closed state. A second magnet is mounted to a moving element where its distance is being sensed. When this second magnet enters the reed switch's sphere of magnetic influence, the contacts will open. This second magnet's polarity must be at least equal and opposite the magnetic strength of the first magnet. Now, when the second magnet is withdrawn, the contact will reclose, completing the operational cycle. As was the case with the normally closed sensor, a magnet is mounted and centered over the contacts for the latching sensor as well. In this case, however, the magnet strength is not strong enough to close the contacts. A second magnet is mounted to a moving element where its distance is being sensed. When this second magnet enters the reed switch's sphere of magnetic influence, the contacts will close. This second magnet's magnetic strength will be aiding the field of the first magnet. Now, when you remove the second magnet, the contacts will remain in their closed state. This occurs because of the natural wide hysteresis of the reed switch. To have the contacts open again requires a third magnet with opposite polarity to the second magnet we used. Also, one can use the second magnet with its polarity reversed if that is a feasible option for a given application. When this magnet enters the reed switch's sphere of magnetic influence, the contacts will open. Removing this magnet, the contacts will remain open, completing the cycle. This is ideal for applications where the reed sensor will be in one or the other state for long periods of time. In either state, the sensor will draw zero power for each latching operation. As we have seen, magnets have unique properties that we can use effectively in the electronics field. There are a wide variety of magnets having a host of different properties. These magnets are being used in an ever-increasing number of applications. They allow us to switch reed sensors without drawing any power. Drawing no power in this power-hungry world is a true asset.